very tender. So we've been doing some research looking at the impacts of various kinds of herbicides on microorganisms. Now, you may hear a lot about pesticides and their impact on human health as a direct toxicity issue. But you probably have heard less about their impact on microbes. The world is facing a crisis, though, with microbes because they're becoming resistant at an alarming pace to antibiotics. So along with climate change, antibiotic resistance is now being touted as one of the world's great crises. We've only had the use of modern antibiotics for about 70 years. And they underpin almost all aspects of our health system. But in addition to those organisms that cause disease, we rely upon microorganisms on our skin and in our gut and in the soil and on the food we eat to keep us safe from those pathogens. So it becomes an interesting and an important question to understand how our technologies influence these various microbiomes, the microbes of the world. And our research has been starting to look at chemicals that are being used in all different aspects of the industrial life, but aren't designed to have anything to do with microbes. So this talk isn't specifically about antibiotics. It's about all those other chemicals in our environment for which we've never studied the intersection between the microbe and that chemical. We live in a highly chemical-intensive world. There are something on the order of 80 to 100,000 different chemicals in commerce. Most of these chemicals have never been tested directly for their impacts, either on humans or on microbes. So we know very little about how these different exposures we have, whether they be contact exposures, inhalation exposures, or ingestion exposures, how they may affect us and the organisms we rely upon to be healthy. Oh, I'm sorry. I guess I was on the wrong one there. Okay. We want to see that. Okay. So pesticides are among these different kinds of chemicals. Now, pesticides are one of the most released chemicals in the world. So these are the top kinds of exposures people, domestic animals, and livestock will occur in their lives. So we dump lots of pesticide into the environment. Now, the U.S. EPA permits up to 200 different pesticides just for lawn care. So we're talking a diversity of chemicals as well as a large quantity of chemicals. Homeowners also use these chemicals. It's not just agriculture. Homeowners in the U.S. might use 10 times the concentration of these chemicals as we might see in farms. And even if you have recently walked through a hardware store, you may have seen the aisles of lawn care products or gardening products. They're all packaged in porous bags so they don't explode. Yet, those vapors that are coming from them are a mixture of inhalation exposure for you. The three biggest herbicides used in the world are based on active ingredients, dicamba, glyphosate, and 2,4-D. Far and beyond all the rest are the glyphosate-based herbicides, and you're going to hear quite a lot about those in this session. This is the active ingredient in the world-leading Roundup herbicide. Glyphosate came to such prominence because of genetically modified crops made to be resistant to Roundup. But because now so many weeds are evolving resistance to Roundup, what's happening is new genetically modified crops are being introduced onto the market that have, in addition to Roundup resistance to herbicides based on dicamba or 2,4-D. you may have up to 3 different herbicide resistances in these crops. So dicamba at 2,4-D use is expected to increase dramatically in the next few years. Our study was looking at all 3 of these herbicides. Now we use a lot of antibiotics, as I mentioned before. So half of all antibiotic use is in agriculture. And, we use a lot of pesticides, we also use a lot of antibiotics. And half of all use of antibiotics is in agriculture. So there's a great intersection as well between herbicides and antibiotics. They are used in agriculture, particularly in intensive agriculture, so that animals can live more closely together. But this also are used in a prophylactic way by putting it into animal feed. So animals are exposed to various levels of compounds that are designed to be toxic to the bacteria. We give animals, particularly in countries like the United States, so much antibiotic that it's recoverable in their manure. And it's recoverable at above what's called the MIC, the minimum inhibitory concentration. So we can recover effectively therapeutic levels of antibiotic in the poo. So that's how much is passed through the animal back into the environment. And of course, what do we do with the poo? We gather it up and we put it on our crops, which we then spray with herbicides. So we have this nice mix of herbicides, antibiotics, and microorganisms. Oh, by the way, for those of you who aren't microbiologists, poo is mainly microbes. So each of you produces about 200 grams of poo a day, all right? It's not a competition, so you don't have to weigh it. And about 99% of that are living bacteria. So this is a nice potent mix of the 3. Antibiotic use is so intensive that you can detect both antibiotics and resistance genes, antibiotic resistance genes in the air. In the United States, in concentrated animal feeding operations, the resistance genes can be detected at something like 10 times the concentration downwind of one of these operations as upwind. So this is just how concentrated our use of antibiotics is and its intersection with agriculture. The intersection is even more complex than that. Many beehives in the world, for example, are now prophylactically treated with antibiotics to help improve the health of bees. But at the same time, the bees are gathering pollen and landing on plants that during the times in which they're sprayed with herbicides. So the hive is now also an intersection between antibiotics and pesticides. But also, if you live in the city, you're not protected. Your neighbor doesn't have to tell you when they spray their lawns with Roundup, or dicamba, or 2,4-D. The biggest selling lawn care pesticide in the world is a combination of dicamba and 2,4-D. Your pet cat doesn't have to tell you when it walks through your neighbor's lawn and then comes into your house and you pet it, and then you put your hand in your mouth, or your child puts its hand in its mouth. So you may get application rate exposures even if you live in the city. What you see here in the lower left-hand corner is a picture from my hometown of Christchurch. This is our big central city park called Hagley Park. And when you come into the park, I was riding my bicycle to work one day, came into the park, and there's a big sign that says, "You are now in Hagley Park." They said we didn't know. And there was a little orange sign tacked to it that says, "Don't go any further, herbicide spraying." And the 2 mothers pushing their pram through the grass hadn't made it to the sign yet. Now, we've known for some time that various kinds of biocides, and pesticides are a subclass of those, can induce antibiotic resistance. So there have been reports already from the 1980s about these chemicals that aren't designed to be antibiotics, but nevertheless are toxic to bacteria, having an effect on causing antibiotic resistance. Yet still, it's only recently that these kinds of observations have been trained to look at things like herbicides. In our studies, we looked at two kinds of organisms, both of which are associated with humans. E. coli, which is a human commensal as well as pathogen. Remember that poo discussion? Most of those bacteria, when you look in the toilet, are E. coli. But also salmonella, which is an important agent for food poisoning and is often carried as well by birds. The way in which we studied the effect of the herbicides on these bacteria was to take the bacteria and put them simultaneously in the presence of a herbicide and an antibiotic. So what you see in this picture, in the upper left-hand corner, is a dilution series. Each spot you see on that plate is 1/10 the concentration of the bacteria from the previous spot. We look at something on the order of about 1 billion bacteria. So that one little dot at the bottom of that plate is telling us there's about 1 billion bacteria in our culture. If we put those bacteria onto just the antibiotic, which is up there, all of them are dead. The antibiotic kills all 1 billion bacteria. If we put them on the herbicide alone, they're all fine. And if we put them on the herbicide and the antibiotic, all 1 billion live. So under circumstances where an antibiotic is powerful enough to kill all 1 billion bacteria, simultaneous exposure to the herbicide protects them. In essence, it's sort of like an immunization against the antibiotic. And it works even faster than the toxicity of the antibiotic. They were not pre-exposed to the herbicide. The first time they saw the herbicide is when they saw the antibiotic, and the protective effect was faster than the lethal effect of the antibiotic. Now, we've seen 3 different kinds of effects. Nothing, so the herbicide has no effect on the toxicity of the antibiotic. A significant increase in the resistance, as I showed you in the picture before. But also sometimes we see an increase in the susceptibility to the antibiotic. So it can both increase or decrease their ability to resist the antibiotic. We see these depending on the organism, the antibiotic, and the herbicide. So here's just an overview of the kinds of observations we have. Those numbers in orange are increases in resistance mediated to those antibiotics on the left by the herbicides in the middle. And the areas in blue tell you when there's no change or a decrease. Now what you see looking at these numbers, for example, now I put little rings around a couple of them to give you the spread. We see a factor of about 2 to a factor of about 6 difference in the change in the susceptibility to the antibiotic. This may not seem like a big number, but a factor of 2 can cause half of patients to, a factor of 2 change in the susceptibility of the organism to an antibiotic can change 50% of the patients getting enough antibiotic. Just a factor of 2 is enough to significantly undermine antibiotic therapy. And what does that mean? That means they have the disease longer, they're infectious longer, and there's an increased chance that they will die. A factor of 6, therefore, is a dramatic change in the potential outcomes of an antibiotic therapy. In this graph, which you don't have to understand, I'm only trying to illustrate what concentrations of the herbicide cause the effect. Now, what we found for these 2 organisms, for E. coli and salmonella, the concentration of herbicide necessary to cause that change in antibiotic susceptibility was usually above what's called the maximum residue limit, the concentration that's allowed to be on human food and usually animal feed. But it was well below the application rate. So any environmental exposure can induce this effect. It was well below application rate. Just on my way here, the first paper I've seen published following up on our work came out. And it's the first in situ evidence that the herbicides are able to cause resistance in the organisms that are in the environment. So this happened to be grapefruit trees that were injected with penicillin, but also in which Roundup was used as a weed control. And what they found was, if they just isolated penicillin-resistant bacteria from the trees, they were usually susceptible or killed also by the glyphosate. But the other way around, if they isolated glyphosate-resistant microorganisms, the same species, at a high frequency, they were resistant to penicillin. And this suggests that the adaptation to glyphosate is influencing their adaptation to the antibiotic as well. So as I said before, the response of these bacteria is within the relevant range of exposures for use. And that's ingestion. If it's inhalation or contact exposures, then certainly there are times when we can be exposed to much higher levels than necessary to induce the response. And why does that matter? It matters because herbicides are everywhere. If we were to test the fabric in these chairs, we would find herbicide residues. Your clothes can have herbicide residues. Your babies crawling around on a carpet are exposed to herbicides. Now imagine that your child is crawling along on the floor and it has an ear infection. Well, you'd probably be treating that ear infection with both antibiotics and pain relief. The cat walks in, or the dog walks in, having just tramped through somebody's lawn, and the baby is petting the dog. Well, what we found is that there's a cocktail effect. Aspirin, for example, and dicamba synergistically work together to induce this effect. So at concentrations that neither aspirin would be sufficient to cause, or dicamba, together they cause antibiotic resistance. So just under the scenarios where it might be relevant, we do find cocktail effects. Okay. So both herbicide and antibiotics are used in high quantities in the modern world. Commercial, these studies were all done with commercial formulations, the real thing, what you're really exposed to, and they induce an antibiotic response in known human pathogens. The effect is significant.